All right, we're now going to have 3 work-in-progress papers. The first paper is from Jeremy Singer. He is a lecturer in computing science in University of Glasgow, Scotland. He has, his research interest lies in program languages and security. He's looking for PhD students and postdoc in his group, so please contact him if you are interested in.
Thank you. I want to start with an apology. As soon as my talk finishes, I'm going to run away to the Memory Management Symposium because I have another talk there. So it's nothing you said, I promise. I want to talk to you about MicroPython and Morello. So I'm going to explain what these two things are, first of all. MicroPython is a very lean, cut-down interpreter for the Python scripting language, and it runs ideally on small-scale microcontrollers. So if you've got ESP32 or Cortex-M controllers, then you run MicroPython on these. It's cut down because it doesn't implement all the features of the Python language. Also, there are vast swathes of Python libraries that aren't implemented. And also, it's a very simple bytecode-based interpreter and doesn't do any high-performance optimizations as you might expect on a desktop or server-grade Python runtime. It's written in C. It's fairly small as language runtimes go, about 300,000 lines of code. And as well as running it on a microcontroller system, you can also run MicroPython just as a standard Unix process by compiling it as a C program on a standard machine. And you can run it as a process-level VM. So that's MicroPython. Give me a wave if you've used MicroPython in the past. Resounding lack of MicroPython users in the room. Okay, never mind. Good. Right. What is Morello? That's the next concept I want to introduce. So this is a real Arm processor, which is an implementation of a research concept. So Arm have actually shipped this research-grade processor, and you can run Morello as a server-class architecture running a BSD Unix-like operating system. Morello implements the Cherry concept, which stands for, here we go, Capability Hardware Enhanced RISC Instructions. And the idea is that in a standard RISC architecture, all your pointers are word-sized bit patterns. So integers and pointers are kind of interchangeable, right? Whereas with this Cherry secure extension, your pointers suddenly become double word width, and you have lots of extra metadata in your pointers that means you can't do abusive things that you normally would to and through pointers. So this is a schematic representation of a Cherry pointer. It's called a capability because it allows you to do some things and doesn't allow you to do other things. So the pointer here is your standard word width address that you can use to address memory. But as well as your pointer, you also have a base that says you cannot access memory below that base address. And you also have a limit, which is offset from the base, and that says you cannot access memory above that limit. So really, you only have a small region of memory, a very fine-grained, this is kind of more fine-grained than page-level protection. This is pointer-level fine-grained protection. Oh, and there's metadata as well. So that says whether you're allowed to read through the pointer or write through the pointer or execute, or whether you're allowed to store new capabilities through the pointer and so on. So there's lots of protection about what you're allowed to do with the pointer. And also, most importantly, there is out-of-band a 1-bit tag. And the 1-bit tag is set if this is a valid pointer and unset if this is an invalid pointer. So if you say, haha, I'll just add a random number to my pointer, then the tag is magically set from 1, if it was a valid pointer to start with, to 0. So you can't kind of abuse pointers in the way that you know and love in C programs or assembler language. So there are lots of microarchitectural implementations, all of which have been carefully addressed in the Morello ARM architecture. I mean, really, it's just an ARCH64 implementation with this extra support for these fat pointers here. So the tag bits to implement pointer validity are maintained in your registers and in your cache and in your main memory. You have new special registers to deal with these fat pointers and new instructions to deal with the capability, so your instruction set has been extended. And at runtime, when you try to dereference a fat pointer, lots of checking goes on to make sure that you really are doing something you're supposed to. So if you try to dereference an invalid capability where the tag is set to 0, you get a fault. A bit like a seg fault, only this is a different kind of fault, but your process dies horribly. Or if you try to access memory and you're accessing memory out of bounds of your pointer, again, you get a fault. Or if you try to do something that your metadata doesn't allow you to do, again, you get a fault. So you can trap on these faults and try and patch things up, but you certainly can't do the illegal memory access you were trying to do. You get a capability exception. So, for systems programmers, you need to forget all those assumptions you used to have, like size of int equals size of int star. That's no longer true. Generally, you probably shouldn't assume that anyway, but you definitely can't on this capability architecture here. You can't cast between pointers and integers, which you generally can do, even in, super safe systems like WebAssembly. No, you can't cast between pointers and integers. And you must ensure that you've got validity in your pointers before you try to dereference them, otherwise you will get a fault. So this is all introductory material here. None of this is my original research. This is all based on research that other people have done to implement this new architecture. But this deals with problems like pointer provenance. Pointers are given to you when you call mmap or whatever in your operating system, or when you kind of create things at boot time, and you can't somehow fabricate new pointers from integer bit patterns that you've randomly created. You can't go out of bounds, so spatial safety is enforced, and you can't kind of use stale pointers, because once you've kind of freed your pointer, it should no longer be a valid pointer. Right, so this is now the start of what I've done and what I want to tell you about for my work in progress here. So we have built MicroPython for this Morello architecture in two different ways. The first way is a hybrid version, which is running as a kind of legacy ARCH64 binary with no fat pointers involved at all, just kind of running in legacy mode on the new architecture. And the other way is, this is called the pure cap, the pure capability mode, which is where we have replaced all the pointers with these new fat pointers and the guaranteed, associated safety guarantees. So we had to make some adaptations to the MicroPython C code base, updating the register save sequences for functions, function calling and returns, updating how structs store bits and bit fields, and also dealing with the tag bits to make sure that your pointers really are valid before you dereference them, capability provenance. But in fact, maybe this is why this is only work in progress, we only had to change 87 lines of code in the MicroPython code base to get something that compiles and runs. I'm not saying it's never going to fall over, but this is a minimal change to get a running MicroPython interpreter in our new capability world. This is 0.028% of the code base, which is very small. And indeed, other people have ported the whole of the KDE desktop to Morello and found that they only had to there we go, a very similar proportion of their millions of lines of code. So I guess when you are porting to this new capability architecture, there's a very small amount of code to change. The complexity is working out which of those lines do actually need changing. So finding that kind of needle in the haystack of the millions of lines of code. There's loads more we want to do. We want to port the MicroPython garbage collector to Cherry. So at the moment, as soon as you do garbage collection, the thing falls over. We want to have tight bounds on our allocator. So now we have these fat pointers. We can say you must only reference memory in this small region here. We want to do that on our in virtual machine allocator. Python enforces software checks on things like, list length and so on, and you can't, reference outside of data structures. Could we replace the software checks with hardware checks using these new capabilities? Could we do software sandboxing of untrusted library code? And could we execute this on bare metal? So watch this space. It's all work in progress, and I shall give you a very quick demo, perhaps. Let's see if I can do this now. So I'm just going to try and access my machine in Glasgow. Oh, no. I'm not. That's because I got my host name wrong, sorry. Good. So that's just my Linux gateway, but now I'm going to go to my Morello server. Woo, here it is here. And I am going to run my MicroPython. Good. So this is my Cherry executable here, which is an ARM64 executable with some capabilities. And now if I say this, right. So this is now a pure capability MicroPython, and I can say, and hopefully, oh no, help, I did it wrong. Right, okay, let's try again. Ta-da! Good. So it's running very simple Python scripts in its safe, pure capability environment. And that's the end of the talk. Thank you.
Let's thank the speaker. Given that he needs to rush to another talk, so let's release him, and then we will prepare for the next talk.